Assalamu alaikum and a very good day to everyone who's watching this video. In this video, we will explore on how to do calculation under the consolidation theory topic. But before we proceed with the calculation, I think it is very important for me to briefly explain on what is actually consolidation. So I will use both English and Malay, and I hope you are okay with it. Okay, so consolidation process is a process where when you put a load, okay, so imagine you have a soil specimen. Okay, so imagine you have a soil specimen like this. Okay, so bayangkan this is your soil specimen, and then this is clay. Okay, clay, tanah liat. So these circles, okay, these are soil particles. Okay, and then the area around the soil particles are, this is void, and since this is saturated specimen, so the void is filled with water, and then you put load on top. Okay, all right, so consolidation process is where when you put load, okay, first the load, okay, beban ini, load will be transferred to the water, okay, the pore water, okay, and then this causes, okay, the load causes the pore water pressure to increase, okay, pore water pressure meningkat, and then water will dissipates, okay, dissipates or will drains, akan keluar daripada this sample. Okay, water will dissipate or discharge from this sample. Okay, so after a long time, the load tadi tu, the load or the pressure put on the sample will be taken by the soil skeleton or the soil solids. Okay. Okay, so over time, okay, remember we have, as I told you, we have load here or pressure put on the soil sample. So over time, over time, as the water gets out of your soil specimen, okay, akan berlaku settlement, okay, so akan berlaku reduction in the volume of the specimen because of the reduction in the volume of water. Okay, so this part we call it as settlement. Okay, settlement of the soil specimen. All right, so that is basically the consolidation theory. Okay, so I will repeat. Okay, saya ulang sekali lagi. Consolidation is a process where when you put a load, okay, you put a load on a saturated soil sample. Okay, in this case, contohnya this is saturated clay samples. Okay, saturated means all the voids. Okay, all the voids within the clay sample is filled with water, diisi dengan air. So we call it saturated. Okay, so when you put the load, water within these voids will discharge ataupun drains out of the voids. Okay, will drains out of the voids. So after some time, we will realize the reduction in the volume of the sample happens because the reduction in the volume of water. Okay, so sample height ni, okay, ni ketinggian asal. So selepas beberapa lama berlaku proses consolidation, you will notice there is a reduction in the height of the sample. Okay, disebabkan oleh air yang keluar daripada soil specimen tadi. Alright, So that is basically consolidation process. All right. And then I think it is also important for me to briefly explain about a laboratory test. There is a laboratory test to determine the characteristics, okay, to determine the characteristics of soils of low permeability, okay. And then the name of the test is one-dimensional consolidation test. Okay, one-dimensional consolidation test. All right, so I just want to briefly explain on this. Okay, untuk test ini, actually for your sample, okay, so let's say you have a soil sample, and then soil sample you itu, contohnya, you bawa clay, okay, you want to use clay, so you bring clay to the lab, all right, and then that clay sample, you have to put it in this ring, the sample ring. Okay, sample ring, this is hollow. Hollow means you can put whatever through the ring, okay? So it is hollow. So basically you will put, let's say you bring your clay soil, okay? And then you put it in this ring, okay? So this is a sample ring, all right? And then when we say ring, okay, so if you make a cross section, so the cross section is circle, okay. If you look at from the top, so the cross section is circle, all right. Okay, so now I think we can proceed with the example that we want to do in this video. Okay, so I took this example from Principles of Geotechnical Engineering book by Braja M. Das. Okay, so it is problem 11.3 under the topic Consolidation Theory. So as we can see, okay, I'll read a bit here. It says here that the following, okay, this table here is a result of a laboratory consolidation test on a sample of undisturbed clay obtained from the field. So basically, jadual ni, this table menunjukkan results consolidation test, laboratory consolidation test ke atas satu soil sample clay. Clay yang ni yang kita ambil daripada lapangan lah, daripada field, okay, in on site, from site. Okay, so this is all the result as we can see. Okay, if you see the first column, this is pressure, and the second column is the height of the specimen. All right, so before we actually start with the calculation, I would like to explain a bit on this data. Okay, what does this data mean? Apakah maksud data ini? Okay, if you look here, for example, so the pressure is 0, the final height of specimen is 1.9 centimeter. So, and then when the pressure increased to 0.25, so the final height decrease, menurun kan, tadi 1.9, so now it is 1.763. And if you notice the trend, as the pressure increases, okay, pressure ni meningkat, you can see that the final height of the specimen decreases. Okay, dia menurun. Alright, so I will explain a little bit on this. Alright guys, so from that table just now, okay, so referring to the previous table which I showed you just now, it says that at 0 kilogram per centimeter square pressure, okay, the height is 1.9 centimeter. Okay, apakah maksudnya? Okay, back to the consolidation test tadi. Okay, this is a soil sample tu kan. Okay, actually we have like a complete setup of the sample, tapi saya nak tunjukkan in brief je lah. Okay, so this is the ring. Okay, this is the ring, and your soil sample is within the ring. Okay, ini soil sample you within the ring. Okay, you put a load at the top. Okay, so untuk test ni, you will first start with 0 kilogram. Okay, so you will start with 0 kilogram, and then you increase the load. Selalunya kita akan doublekan the load. So we will double up the load. For example, we start with 0 kilogram, and then the next load is 1 kilogram. Okay, and then we double. Double means it is 2 kilogram. Okay, so the next one is 4 kilogram, and so on. Okay, so it's obvious to see. I hope you understand this. So normally we will double the load. So when we double the load, okay, of course, it affects the pressure. Ini pressure, ini tadi pressure. All right, pressure. Sorry. Okay, can you see? All right, this is pressure. So we know that pressure equals to, okay, sorry. So pressure formula equals to force over area. Okay, so force. As we increase the force or the mass here, okay, so of course the pressure will also increase. So I repeat, as we increase the mass here, okay, the load, we increase the load, so the pressure also increases. Okay, so sebab tu, that's why if you notice in this table, okay, so the pressure increases. It increases because, okay, pressure increases because we increase the load applied on the soil specimen. So we start with 0, okay, and then we increase to 1 kilogram, okay, and then we double the load, 2 kilogram, 4, 8, and so on. Okay, so that's why the pressure increases. And then okay, back to my drawing here. Okay, so the data means at 0 kilogram per centimeter square pressure, okay, so the height, okay, the height of the specimen is 1.9 centimeter. Okay, and then I would like to clarify here as well, okay, that this sample actually, okay, the circle ones, these are soil particles. Okay, these are soil, and then this area here, it is void, but filled with water. Okay, all right, so this one is equals to this. We can separate this, okay, ini kombinasi soil dengan void. Okay, kalau dalam keadaan saturated ataupun tepu, so the void is filled with water. Okay, tapi kalau dalam keadaan partially saturated, the void, okay, the void can be partially filled with water, and then can be filled with air ataupun udara. Okay, alright, so here we can separate the combination of soil and void to this here, the figure here. Okay, so we can separate, kita boleh asingkan dalam bentuk solid dengan void. Okay, this is to help us with the calculation. Alright, so this is the height of solid, and then up here is the height of void. Okay, and then as we go through the table, okay, so I got this, ini adalah data daripada table, so I'm just trying to explain to you the meaning of the data before we proceed with the calculation. Okay, so tadi pressure is 0. Now the pressure is 0.25 kilogram per centimeter square. Okay, so it's the same thing. As you notice, okay, as the pressure increase, nampak 0 ke 0.25, the height of the specimen decrease ataupun menurun. Tadi 1.9 and now it is 1.763 centimeter. Why do you think? Okay, kenapa agak-agak? So kenapa we have to go back to the principle of consolidation, which I have explained to you earlier. So with consolidation, it is the water that is getting out of the soil specimen. Ingat tak? Kita letak load, okay, we put the load on the saturated soil sample. So it is the water, okay, it increases the pore water pressure, and then that pore water pressure will okay, will get out of the soil sample. Okay, so bila water to gets out, so berlaku reduction, okay, or the sample is compressed. Okay, it is compressed, so sebab tu dia punya height dia makin decreases lah, makin menurun as the pressure increases. All right, and it's the same thing, okay, until the pressure given in the table, which is 8.0 kilogram per centimeter square. Okay, so explanation dia sama. All right. Okay, I hope you're clear so far with my explanation. Now we will proceed with the calculation. If you notice, I leave like a blank space here. Okay, so these are the only data given. So I leave a blank space here. This is actually for our calculation. Okay, so first, what do we have to do? If you refer to my lecture notes on consolidation theory, which I have uploaded to the e-learning, if you look at the steps, okay, first we have to calculate the HS, or the height of solid. Okay, it is here. I'm so sorry, I think I will draw again to you. I'm sorry for my messy drawing. Okay, so as I told you just now, this is our soil sample, and then we can divide it into the solid parts, okay, as well as the void part. Okay, we mentioned void because the void can either be filled with water or air. It depends on the specimen. All right, okay, so back to this. So what is HS? Which one is HS? HS is this part, okay, this part. This is HS. Okay, this is the height of solid, and then up here, obviously, okay, I'll put it this side. Up here, obviously, this is the height of the void. Okay, ketinggian solid is here, ketinggian void is there. Okay, and then basically it is very simple. You just put all the raw data into this formula. Okay, please refer to the lecture notes. Okay, so it depends on the unit that you want to use. Okay, so here I'm going to use HS, or the height of solid, equals to mass of the dry specimen over area of the specimen. GS is the specific gravity, and then this is the density of water. And then before I forgot, I would like to highlight the data given to us. Okay, so these are the raw data given. So let's look. So the height of the specimen at the beginning of the test was 1.9. Okay, you don't have to worry about this. It is just telling you that at zero pressure or zero load applied, okay, so the height of the specimen is 1.9. All right, and the diameter was 6.35 centimeter. Okay, so the diameter of the ring, okay, remember the ring that I showed you just now, which is this ring? So the diameter given is 6.35. Okay, I'm sorry to shift back and forth. All right, the next raw data given is the mass of the dry specimen, which was 91 gram. And then also given the specific gravity, which is 2.72. All right, and then here is the questions. Okay, so you have to make calculations in order to draw an E versus log pressure curve. Okay, so E, what is E? E is, okay, I draw here, hope you can see. E is the void ratio. E is the void ratio, and what is it? Pressure, effective pressure. So sigma is the effective pressure. Okay, E versus effective pressure. All right. Okay, so back to this. So you put all of these raw data in here. Okay, so you put all of the highlighted raw data here into this formula. Okay, and then you will get HS equals to 1.06 centimeter. Okay, you can try, do this, and then you'll get this value of HS. Okay, so HS equals to 1.06 centimeter. okay? And then HS is constant, okay? HS is constant. The height of solid is constant, okay? Why? Because when we go back again to the principle of consolidation, we know that the reduction of height, okay, of the specimen, it is because of the reduction of the volume of water. Okay, water gets out of your specimen, get out of the pores. Okay, not the solid, right? Okay, so that's why the height of solid is consistent, which is 1.06 centimeter. Okay, so the second step is we have to calculate the height of void. Okay, the height of the void, which is this one. All right, we have calculated the height of solid, 1.06, and this is constant. Okay, and the next one is we have to calculate the height of void, and the formula given, you can refer to the lecture note, is h, which is the total height. Okay, minus hs, which is the height of solid. Okay, h is this one. Okay, each of these are the h at the different pressure. So the h for this one is 1.9. Okay, so at 0.25 pressure, the height is 1.763. Okay, and so on, and until the pressure of 8.0 kilogram per centimeter square, the height of the specimen is 1.550 centimeter. So okay, I'll show you the first example. Okay, here, in order to calculate V equals to H, which is 1.9 minus HS, okay, the constant one, which is 1.06, okay, 1.06 equals to 0.84, okay, and then this one, 1.763 minus, okay, I'll write again here, 1.763 minus 1.06 equals to 0.703, and you can do the rest. Okay, you can complete this column here. Okay, so this is the complete data that you will get for HV, or the height of void. Next, we have to, okay, please refer to your lecture notes. So step 3 is we have to calculate the void ratio, or E. Okay, so we have to calculate the E, or the void ratio. So E note here is the initial void ratio, equals to HV over HS. HV is the height of void. Okay, again, height of void over height of solid. Okay, and then I have done the first one to you to see. Okay, so it's very straightforward. It's very simple. So HV here is 0.84. Okay, over HS is the constant value, which is 1.06. Okay, and then you get the initial void ratio, or E note, is 0.792 for zero pressure. Okay, and then you can do the rest. You can complete the table. All right, so this is the complete data for initial void ratio. Okay, so yeah, this is the data. Okay, you should get these values if you do this correctly. All right, so what is the next phase? Okay, the next phase is we're now answering the second part. Okay, the first part is we have to make necessary calculations. Yes, we did already. And then this is the second part where we have to draw an E versus log pressure curve. Okay, so we have E data, okay, or the void ratio data, which is this one. So I'm going to highlight this. Okay, so we have this. Okay, and then we also have the pressure data, which is already given to us. So which is this one. All right, so now we have these two data, then we can proceed with plotting the curve or the graph. All right. Okay, so we have all the data that we need. Then we can proceed with drawing an E, which is the void ratio, versus log effective pressure. Okay, curve. Okay, so why log here? Okay, so I just want to explain. Maybe some of you or all of you know about this log already, but I think it is important for me as well to explain a little bit on what does log curve means or semi-log curve means. Okay, before that, I'm going to show you what I have plotted. Okay, so E is on the y-axis, and effective pressure is on the x-axis, and then this is my graph. Okay, so this is my graph, right? I think you cannot see the whole thing, but I'll try my best to show you. Okay, so again, on the y-axis, okay, so this is my y-axis. This is E, or void ratio, okay, void ratio, or E. Okay, and then for the y-axis, okay, it is my effective pressure. Effective pressure, this is log scale, okay, and then I have also plotted all the 7, I think, so we have 7 points, okay, here. So 1 2 3 4 5 6 7. So okay, we have 7. 1 2 3 4 5 6 7. Yes, 1 2 3 4 5 6 7. So we have 7 points for this graph. All right, so so what is it when we say semi-log graph? Okay, semi-log means, so we have two axes, right? So we have y-axis and x-axis. Semi-log graph means one of the two axes, the scale for each box is different. Okay, the increment is different. It's not consistent. Okay, so in this case, our log scale axis is the x-axis, which is the effective pressure axis. So this is log scale. If you notice, okay, I think it's easier to show the y-axis first. If you notice, for the void ratio axis, it is consistent. So the increment is consistent. So 0.3, 0.4, 5, and so on. Okay, and then for each of the small box, okay, so we're from 0.3 to here, so the increment is 0.005. okay, 0.005. Yes, okay, so that is the y-axis for the void ratio axis. Okay, so this is not a log scale. Okay, this is like just a normal scale. But here, if you notice, for the x-axis, okay, this is the log scale, means the increment of each of the small boxes is different. Okay, as you move to the right. Okay, if you see here within this range from 0 to 0.25, so the small box, it is 0.025. So that is the increment. Okay, and from 0.25 to 0.5, it is still the same. The increment, okay, of each of the box here is 0.025. But when you move from 0.5 to 1, okay, you can see that it changes already. So one box is 0.05. Okay, so, and then you move on to the right. You can see here, for example, between 4 and 8. So each of the small box, the increment is 0.4. Okay, so it's not consistent. Okay, it is not consistent, so that it is called a log scale graph. Okay, but in this case, since just one axis, okay, only this x-axis has a log scale graph, while the y-axis is just a normal scale. So that's why we call this as semi-log graph. Okay, I'm gonna write here for you to remember. We call it semi-log graph. All right, so this is just it's not part of the calculation, but I hope it can make you understand better, inshallah. All right. Okay, so we have all the points now. So now we just want to connect all the points together with a line. All right, everybody. Okay, so it is something like that. Okay, so you don't have to connect all the points, but you do the best fit line. Okay, if you go to Excel, it's easier if we use Excel. Okay, because in Excel we can use the best fit lines. Okay, for all the points, means it's not connecting all the points with a line, but it's like making a line where the distance, okay, the distance from this line to each of the point is the closest. Okay, so this is my best fit line for this manual graph. This is not Excel. Okay, so basically we're answering the second part of the question. Okay, so yeah, I'm gonna highlight here. Make necessary calculations. Okay, so we did this already earlier, which is the table. And then the second part is draw NE versus log effective pressure curve. Okay, E is void ratio versus effective pressure curve, which is this one. Okay, so basically we have answered the questions. Okay, we have answered the question asked to us. All right. Okay, all right, so we've done answering the question given. Okay, but I think some of you or all of you might be wondering, okay, so we have draw the graph, kita dah lukis graph, okay, E, over ratio versus effective stress. Okay, so we're done with it. So now what? Right? So after plotting this graph, so what is the purpose of plotting this graph? Okay, some of you or all of you might be wondering, okay, which is a good question. Okay, we just don't plot it and leave it like this. Okay, bukan kita just plot and that's it. No, actually, from this graph, void ratio, this is an extra information for you. I mean to you, extra knowledge. Okay, from the void ratio versus effective pressure graph, okay, from this graph, we can actually determine the compression index and pre-consolidation pressure. Okay, the value of compression index and pre-consolidation pressure. Okay, this is important for the future works. Okay, but however, we because of the time constraint, we don't cover this in our lecture this semester. Okay, but if you are curious to know about all of this, so you can feel free to Google and to find out more about the usage of this graph. Okay, which is to determine the compression index as well as the pre-consolidation pressure. All right, but however, back to our question, we're done here at this level. We're done with, I mean, we just have to plot the void ratio versus effective pressure graph. All right, so yeah, that's all. I hope you understand the video. Okay. And then if anything, please feel free to text me for further discussion. And I wish you all the best, okay, for your final exam. Thank you very much for listening. Assalamualaikum and bye-bye.